Hello, everyone. We will get started now. Welcome to Advances in Emergent Needs in Paleo-Geoscience Cyber Infrastructure, a webinar series organized by C4P. C4P, Collaboration and Cyber Infrastructure for Paleo-Geosciences, is an EarthCube research coordination network supported by the National Science Foundation. I'm Leslie Shee, and I'll be the moderator today. In today's talk, we have one presentation, about 20 minutes, with time for questions afterward. If you have any questions during the presentation, just send them through the WebEx chat window, and I'll read them aloud after the presentation. You can send a question in at any time. All presentations and the follow-up discussion will be publicly archived on the EarthCube website and at the C4P YouTube channel at youtube.com/Cyber4Paleo. Our speaker today is Liz Bradley from the University of Colorado, and she'll be speaking about CScibox, a software system for age model construction and evaluation. So Liz, please start when ready. Liz, can you check to see if you've unmuted yourself or changed anything with your audio? I can see that you are speaking. Maybe try one more time, and if others can hear Liz, then just let me know. I don't know if it's just my problem.
I'll take off the headset.
Oh, okay.
Now
yes,
can you hear me?
I can hear you now, and it's clear.
Okay, then we'll just go without the headset. Okay, let me try the camera again. Can you still hear me?
Yes.
Okay, good. So what I'm going to do today is tell you about a software system that is designed to help you build age models from paleo records, from cores. And my ulterior motive here is that you actually start using this software. So I'm not going to give a standard research presentation with lots of PowerPoint slides. Rather, I'm going to focus on a demonstration and answering your questions. Now, when somebody is showing you software that they wrote, it's kind of like watching a teenager fix the settings on your cell phone. It goes so fast that it's all but impossible to replicate, and you're just hoping that the darn thing will still work when you next touch it. And this demo will probably feel like that. But our web page, which you should be seeing right now, can you see that, Leslie?
Yes, it's
okay,
showing
good.
your screen.
All right, so our web page has, in addition to kind of some words about the project, it has some screenshots which will help you replicate what I am going to talk about today in the demo. It has also some pointers to places where you can get the code. It has listings of who's involved. It has some papers. We don't have a lot of papers because we've been busy writing code. And it has a page of demos and tutorial videos, which should be able to help you. One final note before I dive in. This is not software built by a well-funded commercial entity with a ton of well-paid software engineers, and it is still very much under development. It's actually quite unusual in the computer science world to release software like this to a user community. We're doing it because our goal is not to build academic software that runs once, but something that actually helps people. And what that means is that the software may actually fail on you if you try something that we didn't think of and we didn't test. But when you send us a report of such an error, we will fix it, and we can add useful features that you think of. So I hope this interactive process will help both you and us. So I'm going to start with a couple of slides. The system is called, as Leslie said, CScibox. The goal is to help scientists build age models and from lots of different kinds of cores. The underlying idea of this project was to bring serious computer science to this table, that is, to cross-pollinate earth science and computer science around the task of age model construction. The team that is involved in this project is listed on this slide. It includes a mix of computer scientists and geoscientists. Jim White does ice cores. Tom Marquito does marine sediment cores. Ken Anderson is one of the CS people. He's about software engineering. That's the part of computer science that worries about things like databases, interfaces, where the code runs, and so on and so forth. My personal background and my interest in this project is actually not instantiated in the version that I'll be showing you, but it's our ultimate goal. That's artificial intelligence. Right now, CScibox takes all of its orders from the user. That is, it executes his or her step-by-step instructions about the workflow, the scientific workflow, to be used in the agemodel construction process. The AI system is going to wrap around that part, acting autonomously. So it's going to make intelligent choices about the steps in the workflow based on the data, the situation, the intermediate results, and so on and so forth. So for example, if you were confronted with this agemodel, you might ask yourself, is that because the core got worked around? Or did the lab mess up on that sample at 40 centimeters? Or did I make a bad choice when I invoked Fakin? And what would happen if we tried a different calibration curve? So these are steps that you go through probably when you're looking at agemodels. And our AI system, which is under construction, does that kind of thing and presents the results to the user with a narration of all of its reasoning that's involved. Now, the current version of that is way too buggy to release, but that's where we're going. So I'm going to move to a demo. Here's what the user interface of CScibox looks like. The code ships with several cores for you to play with, which are up here in this drop-down. Let's select one. This is one of Tom Marquito's cores. And you see a bunch of columns. The left-hand column is the depth of the sample. Samples are the rows. The second column here, computation plan, that is the scientific workflow. That is the series of analysis and computation steps that were used to produce the data that you're seeing. In this case, for this core, the computation plan, the workflow that was used to kind of pull this data in, is just the input workflow. In the previous core that I had up, I had already run a scientific workflow on these data. So you see the name of that workflow, that plan in that column. That workflow, which I can look at using the computation plan browser, performs a reservoir age correction and then a Calob style C14 calibration using the Cal 13, Marine 13 calibration curve. Now currently I have these data sorted by depth. By clicking on a column header, you can change that from upward sort to downward sort. You can also click on a different column header if you'd prefer to sort on that column instead. But normally, one would sort presumably on depth. Excuse me. By the way, this is part of what I mean about software engineering and user interfaces, this way of presenting the data and the scientific workflow in ways that that don't require you to do any coding, that don't require you to do any slinging of data, and ways of interacting with that stuff that are easier. CScibox ships with a whole bunch of plans. You can also roll your own, and you can import new calibration curves if you want using this tool that I won't actually demonstrate unless I get some questions. So back to this core. We haven't done anything yet to these data, so there are lots of nones over here. The stuff in the calibrated age column, by the way, are tephra dates. The stuff in the 14C age column are dates from, let me see what this is. This forum species, right there, G. ruber. What you saw me do there, by the way, was change what data are visible. There's a ton of information under the hood here, and it can easily get overwhelming. The GUI, the graphical user interface, lets you tailor what information you see using the little icons that look like columns and rows. Okay, let's run a calibration on this core. This little button right here runs a scientific workflow on the data that's in the workspace. So I hit it, I get a drop-down that lets me pick from the computation plans that are in there. So let's run a very simple one. that just bounces the calibrated ages off the IntCal, I don't remember which one it was, IntCal 2013 curve. Now this entire column has been filled in. Let's plot those results. This is the plotting icon right here. You click on that, and CScibox will plot the data that's in your workspace. And we probably want to plot calibrated age versus depth, like that. If you prefer your age models with the other way on the axes, you can select that with the drop-downs and change your axes around. There actually are error bars on these points. You can maybe see them kind of sticking out either side of this icon here. You can plot multiple things. Maybe you might like to plot the raw and calibrated ages on the same plot. Looks like that. Actually, it looks like the legend is broken. I'll have to fix that. These are the calibrated ages, and these are the raw ages. Excuse me. Now, this thing is a Marine Corps, so we actually should be using a computation plan on it, like this one, that does a reservoir age correction before doing the Calob style conversion. So let's run that one instead by selecting it. Now, CScibox is asking us what reservoir age correction it should use. You can type in the numbers if you want, or you can type in the latitude and longitude where the core was harvested. This one was from somewhere around here, I think. So I type in the lat long. And what CScibox is doing is it's looking through the 14 chrono database of reservoir age corrections, and it's looking at the lat long of the sample that you entered. It's looking for the closest place where it has a recorded reservoir age correction. It's plotting both of those on a map, and it's offering you the option to either reject or accept that selection. I'm going to accept that selection, and the data are now in the workspace. Excuse me. You can also reject that selection, enter the numbers yourself if you want. We've now run two different calibrations on this core. Let me expand the view, that is the rows, to show all of them. And now what you're seeing is, for this sample at 356 centimeters, there are two different calibration plans, two different computation plans that have been applied to that sample, producing two different ages. We can plot all of this stuff, like so. And you can see the, let's see, the red ones are the without the reservoir age corrections, and the blue ones are with the reservoir age corrections. The tepras don't get corrected or calibrated, so they don't move. Now, an important point about these computation plans, they are metadata. They are stored along with the data. That's why they're in this second column of the computation plan. A computation plan is a complete record of what was done, which makes everything transparent and repeatable and redoable if, for example, IntCal releases a new curve. If that happened, you just look through your data, filtering it according to different calibration plans, computation plans, my apologies, see which data had been processed using the curve that's now gone out of date, and then you could build yourself a new computation plan that's kind of like the old one, except, excuse me, it maybe uses a different plan. So Calob plus some other IntCal. And there are a bunch of supporting data sets built into this tool, and you can choose whichever one you want. Again, you can import your own if you want. And now that computation plan, that scientific workflow that you just built, is up here. It's also available in that drop-down, so we can run it. And we can enter whatever numbers we want here. I'm not a geoscientist. I don't know if these makes any sense, but there they are. There are the results. And now there should be 3 different dates for each sample here. You can also, by the way, build a completely new plan with that Computation Plan browser, which I can show later if people are interested. Okay, how do you import your favorite core into CScibox? Let's say I have some data in a CSV file like this. I can suck that into the workspace using the importer. You can also export things, but I'm going to show you the importer. And that brings up, I think it's on my desktop. There it is. Our import wizard. The import wizard allows me the option to name the core. I can add it to an existing core. I can add the data that comes into an existing core. I can create a new one. What's going on here? These names here are the names that CScibox found in the headers of the spreadsheet that you gave it. So that's what's over here. What's over here is its guess at how to map that particular term to its own internal variables. That's why it's called a wizard, because it's making those guesses. Here it managed to figure out that sediment depth, paren, cm, close paren, should be mapped to its own internal variable that's called depth, and that the units should be centimeters. So it did pretty well there. It was not able to guess what 14 ch paren BP close paren meant. That's actually something that's quite hard for computers and quite easy for people. That's the field of natural language processing. So we have to help it. And we do that with this dropdown. And what's in the field of this dropdown is all the internal variables for CScibox. And probably 14ch should be mapped to 14ch. Now in this spreadsheet, there was a column of error that's associated with this value here. So error associated with this 14ch. So we can tell CScibox that by saying map the error column to error in this variable. And the last thing was sample type. That looks like the kind of stuff that was dated. See if we can find something, maybe material dated. There. Finish, and there's the data. And then we can run whatever we want on it. This is actually quite useful. One of the real banes of data, as you probably know, is that there's no systematic naming or formatting scheme, and this is a way to address that. I've showed you only sediment core examples so far, but CScibox works with any sort of depth sorted record. We have a chunk of the North Grip ice core in here, which is a little bigger, so it takes a while to come across. And we also have a computation plan that runs a particular ice core flow model that we can apply to that core. So let's do that. It's going to ask me for some parameters that it needs to set up the model. And I've looked them up. Off it goes. They're filled in. And here's the flow model age that was produced by that flow model acting on these data. We can plot them. And there's the age model. We're working with my Winstrup from Copenhagen to add her layer counter to the toolbox here. She uses hidden Markov models to count layers, to figure out where layers are. Now that brings up a larger design issue. People in this community have written lots and lots of good code. So we decided to build in a kind of docking port to make it easier to plug in chunks of code to CScibox. And what that means is that to get your favorite tool to appear in the drop-down in the Computation Plan browser of your copy of this code. That's not easy computer science, by the way, but we think it's worth it. It has lots of advantages besides us not having to reinvent wheels and you being able to customize the code. One huge advantage is that when you do this, your code automatically inherits and can make use of all of CScibox's GUI stuff. And eventually, CScibox's AI system will be able to use your tools to reason automatically about age models. One of the things we're working on is putting Bacon as a plugin. And as you know, if you use Bacon, choosing appropriate parameter values for it, invoking it, and interpreting the results can be a bit of a challenge. And our AI system is going to automate that. It could also automate doing things like running a layer counter in the top of an ice core, then figuring out when the results are getting iffy and switching to a flow model. I said something about your copy of the code. All of this stuff is available on GitHub, open source. It's not completely trivial to install this source code, however, so we also have one-click installers for a variety of operating systems, and you can find those here. Okay, so I've given you a lot of information, probably way too much. Here's the project webpage that I was showing you before, excuse me, which has links to the Git repository where you can get the code and the installers, as well as those screenshots, short instructional videos, papers, and so on and so forth. So that's 20 minutes, and I was hoping that that gives you a basis for questions that I can answer or demos that you'd like me to do.
Great, thanks a lot, Liz. So again, if you have any questions, just go ahead and type them into the chat. We can start off with one here.
Okay.
Liz, so we're just wondering, this partnership between geoscientists and computer scientists is great. And what were the hardest concepts to understand as a non-geoscientist when building this tool?
Okay, good question. This is actually the second project that I've led that has used software engineering and artificial intelligence to automate and facilitate a task for geoscientists. And the hard thing about both of those is learning each other's language, and that shouldn't be any surprise to anybody. And it's not just words and concepts, it's also assumptions. Again, I don't think that should be a real hard thing for anybody. Does that answer your question?
Yes, if you have any specific examples of specific, geologic concepts or something, just to give tips to people who are trying to explain a problem fully to a non-specialist, that would be helpful too.
The baseline assumptions that you make, you have to remember that the other person doesn't have those. So I had a particularly embarrassing demonstration at the National Science Foundation of the software that had an age model that was backwards, that is, stuff that was deeper in the core was younger, because I hadn't bothered to tell my grad student about a particular minus sign. We're familiar with this in artificial intelligence. This happens all the time. If you're trying to do what's called qualitative physics, you're reasoning about the physical world, it's very hard to remember those things that we have way in the backs of our heads and we never think about. So, for example, that gravity points down. I've seen qualitative physics systems that didn't have that built in, and all heck broke loose. So, as an artificial intelligence practitioner, the real challenge is what's called knowledge engineering. And what that means is sitting next to a scientist and asking them a series of infuriating questions about the analysis that they're performing that's designed to go all the way back to the bedrock assumptions. Because if you're going to explain something to a computer, you have to give it every single last stupid little bit of information that you would never think of explaining even to a graduate student or a first grader. So there aren't any, there's a whole field of artificial intelligence called knowledge engineering, and there are, it's just well known to be very hard, and you really have to embed the computer scientist with the geoscientists, and I don't think there are really any shortcuts for that.
Okay, that's a great example. The next question is, what are you doing? Okay, sorry, it's a comment and a question. So first, what you're doing seems to align with the goals of the NSF S2I2 program. Have you engaged with any of the NSF S2I2 Software Institute conceptualization efforts?
So I've talked to Barbara Ransom, and I'm planning to send a proposal in to that group in February. The problem is, and I kind of alluded to this, and I guess this is part of an answer to your other question as well. It's very hard to simultaneously do novel research in geoscience and in computer science. And so we are sometimes in the position of having our students, our PhD students who are working on this code, doing stuff that is not necessarily going to lead them to a PhD thesis or a paper in computer science. And that is a little bit of a roadblock with the software institutes, because we want our PhD students who are working on this to be getting research results that will help them in getting computer science jobs. So it's not completely easy, again, to do interdisciplinary work for a number of reasons, and this is one place where that happens. So probably when I write that proposal, I will not write grad students into it, I'll write in programmers. But I'd much rather work with grad students, they're more fun.
Okay, thanks. The next question is, what is the main advantage of CScibox compared to CLAM or Bacon? Is it simply the GUI?
So CScibox duplicates everything that CLAM does and has for about a year now, but the GUI is much better. CScibox, and that's one thing. So it's a kind of professionally software engineered version of this that's built on top of a real database that can incorporate huge ice cores or 20 sample long sediment cores. So it's built to kind of like it's a 747. It can carry one person or it can carry 200 or 300. So it's engineered to be extensible. It's engineered to be useful out of the box. The Bacon question is also really interesting. And part of the answer there is, well, first of all, Bacon does, and CLAM too, Bacon and CLAM do a small subset of what CScibox does. But Bacon, as I said, it does some really cool artificial intelligence reasoning, and it has 4 key parameters that you have to set up to get it to work really well. And to set those parameters, you need to know something about AI and something about geoscience. And very few people have the knowledge to do all that. When I talked to Martin Blau in May, he said to me, he kind of wrung his hands about that, and he said, everybody always just uses the defaults. So there are 4 parameter values, and everybody just uses the defaults. And so what we're doing is we're working with Martin to take Bacon and embed it in as a plugin in CScibox. And that has a bunch of advantages. First of all, then CScibox, in wrapping around Bacon, gives you a front end to it and a back end to it. So you don't have to mess around with plotters. You don't have to, with a separate plotter. You don't have to mess around with separate data importing things. But what's really interesting to me about that is the AI system will look at the data, will look at the reasoning steps that have been done so far, what you've done, and it will use that information to automatically make those hard choices about what parameters it should fire Bacon up with. So part of the answer to that is both of those tools are things that whose functionality is a subset of what we've got. But the other piece is the wrapping it in real software engineering and wrapping it in real artificial intelligence.
Great, thanks for that answer. And we have another very similar question. Do you have any comments about other age model software, CScibox, as compared to other software such as Bcron and Calob?
Yeah, so again, we duplicate Calob. Bcron has some assumptions in it that we don't actually duplicate yet. So Bcron and Ocala can handle accumulation rate distributions that, for example, Bacon can't. And right now, we are pretty much planning on using Bacon for that particular functionality. So it would be very hard for us to plug in Bcron and Ocala because those are both they're not open source. Basically, Martin is willing to share his code, so we're able to kind of take that code and incorporate it in CScibox. But Ocala and Bcron, that's not the case. So I believe, a computer scientist. I believe in open software, open source. And I think that encourages collaboration, and it, I hate the word synergy, but that's what's going on here. We can plug Bcron, well, maybe we could, if we could, plug Bcron and CScibox together, it could amplify things.
Great, thanks.
And by the way, there was, I don't know if you guys can still see my screen, but one of these cores, the data that it came in with, somebody had already run Ocala on it. So that was an input column in the spreadsheet. So then you're able to pull that in and see how different computation plans that you might define or that we might have shipped with it would line up with Ocala or with Calob. So Calob, I think someone ran Calob on this. Yeah, there we go. So here's what Calob came up with for this core. Here's what this particular computation plan came up with for this core. So it's in the same range. So that was one of our first tests, was to compare the results to Calob and Ocala.
Thank you. There is another question, which is, could someone use the program to match depth and age of other types of radiometric data? And if you need clarification on the other types, we can get more information about that.
Yeah, considering I'm not a geoscientist, I could use some clarification.
Okay, could you, could the asker of this question, you can either type in what other types of radiometric data you're talking about, or unmute yourself and make a comment. While we are waiting, we also got a question of the best reference to Bacon. Would that be a paper by Blau?
Yes, Martin Blau is the authority on that. This is good software and it's a great algorithm, and it's just been a pleasure to work with him. So if you Google like Bacon, I think the first thing you get is the Bacon user manual.
Yes, I found that. So I just added that to the chat. Okay, sorry, I also need help in coming up with some other types of radiometric data. So just the different argon dating, potassium argon dating, other types of dating.
Right. So CScibox is built so that you can incorporate your own code, and you can also incorporate what I call background data sets. So in the tools editor, there's a supporting data sets thing. And what that means is you can import some sort of curve that on one axis has something and on another axis has something else. So in IntCal, one of those is raw 14CH and the other is calibrated 14CH. So if you had some radiometric data that needed some sort of processing, that needed to be bounced off a curve like that, kind of like Calob bounces 14CHs around, what you would do is you would have to figure out what curve to import. You would import it using this tool, and then you would build a computation plan that essentially bounced the data off that curve. I hope that answers the question. If it's something much more complicated, then we also have facilities, although they're not completely debugged yet, for people to write very small chunks of code and kind of plug them in. So if there's some small chunk of code that you have that has the input that you want for your radiometric data and the output that you want, then you can just kind of plug it right in.
Thank you. The questioner says that does answer the question. Okay, next question is, how computationally intensive is it to run these age models? Do you run this on a small number of cores, or would it make sense to run this on multiple cores?
That's actually one of the interesting software engineering cyber infrastructure angles on this project. I'm running on a Mac Air, and you saw how fast it returned that ice flow model, which was many, many thousands of points in the North Grip ice core. So things are pretty fast. But if you need more data storage, or if you need more computational cycles, the software is designed to parallelize across cores, across clusters, or across the cloud, or across huge computers. So it's engineered so that it takes full advantage of modern cyber infrastructure. We haven't tested that yet because we haven't had a big enough problem that basically was anything close to frustrating on our Mac laptops.
Okay, great, thank you.
And if you know something about words like Hadoop and things like that, there are software engineering frameworks for parallelizing effort and data storage across multiple platforms if you do the design right. So for example, we use a database called MongoDB. We also have a version that uses HBase, which can scale to clusters. And at one point, we had written a version that stored all of its data on the cloud, as well as did some of its computation on the cloud. We found that that wasn't useful because people like to work on airplanes when they don't have web access, so we went back to a version that does all the computing and all the data storage locally, but it's very easy to scale that out.
All right, we have one more question here so far, which is, what is your ideal vision for CScibox in the future, and is there anything that the C4P group can do to help you meet that?
Okay, so my vision is that, again, I'm the AI person here, and my vision is that this tool does the dirty work for you. It sits there on your computer and tries out all sorts of possibilities. Should I use this curve? Should I use that curve? Should I use a reservoir age correction? What reservoir age should I use? Where should I move from simple layer counting to an ice flow model? Has there been a reversal? And it goes through all those scenarios, it evaluates them, and it presents them to you together with its arguments, its reasoning about what made sense and what didn't. So that's where I want to get to. Where the C4P community can help me is, or help us, because there's a team of us, is by downloading and using the code and finding what works and what doesn't, telling us what works and what doesn't, and also perhaps, and this is a bit of a challenge, being available for that knowledge engineering process where one of us would come and sit at your elbow for a couple hours or a couple days and say, wait a minute, why did you do that? Why did you use that curve? What did you look at in that data that made you do that step next? And all that information would get distilled into rules that would be the firewood that goes into the engine, that's the AI engine in the middle of CScibox. So mainly the thing that people can do to help us at this point is download the code and use it and tell us what you see. Tell us what you like and what you don't.
All right, well, definitely help to get the word out and try to get some more users and feedback for you.
And again, I'm happy, and my students can chip in too. We can set up screen share sessions over Skype if you run into snags. Happy to help.
Okay, well, this has been a really great discussion today. I'd like to thank Liz again. This webinar will be available later both at the EarthCube website and on the C4P YouTube channel. And we will resume the webinar series again in early 2015. So thank you very much for attending and hope to see you next year. Thanks a lot, Liz.
You're welcome, and I'll be at AGU, by the way, if people want an in-person demo.
Okay, great. We will get in touch with you if anyone contacts us.
Okay.
Let you know.
Thank you.
Thank you, everyone.